Once again, welcome to chemistry classes by Vijay Kumar Sethi. Class 12th chemistry. We were discussing chapter coordination compounds, and in this video we will discuss some definitions of some important terms pertaining to coordination compounds. First one is coordination entity. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. For example, like this COCl3NH3 whole thrice is a coordination entity in which the cobalt ion is surrounded by 3 ammonia molecules and 3 chloride ions. Some other examples of coordination entities are NiCO4, PtCl2NH3 twice, FeCN6, CONH3 6. Okay. Coordination sphere. The central atom or ion and the ligands attached to it are enclosed in square bracket and is collectively termed as the coordination sphere. The ionizable groups are written outside the bracket and are called counter ions. For example, in the complex K4FeCN6, the coordination sphere is FeCN6 square bracket 4 minus, okay, and the counter ion is K plus. Now, there is a little difference between these two terms, coordination entity and coordination sphere. What is the difference? Difference between coordination entity and coordination sphere. If enclose the coordination entity in square bracket and indicate the net charge on the coordination entity, then it is known as coordination sphere. For example, this FeCN6 in square bracket having 4 negative charge, this is the coordination sphere, and if we write only this is FeCN6, that is known as coordination entity. Simply we can say coordination entity is present in coordination sphere. Another term is central atom or ion. In coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical arrangement around it is called the central atom or ion. For example, these are the some coordination entity or ionization sphere. You can see NiCl2H2O4. In this case, the central atom or central ion, that is Ni2 plus. Okay, and in this COClNH3 plus, the central ion is CO3 plus, and in this case this is FeCN6 3 minus, the central ion is Fe3 plus. Okay. These central atoms or ions are also referred to as Lewis acid. Actually, what are Lewis acids? The species which can accept a pair of electron is termed as Lewis acids. These central atoms accept the pair of electron from ligands. Okay, that's why these are referred as Lewis acids. Ligands. The ions or molecules bound to the central atom or ion in the coordination entity via coordinate bonds are called ligands, and these are Lewis base because they donate pair of electron to the central metal atom or ion, because these are electron donor Lewis base. These may be simple ions such as Cl minus, small molecules such as H2O or NH3, large molecules such as NH2, CH2, CH2, NH2, or N in square bracket CH2, CH2, NH2 whole thrice, or even macromolecules such as proteins. Types of ligands. Ligands can be classified as unidentate ligand, didentate ligand, polydentate ligand, chelate ligand, and ambidentate ligand. We will discuss one by one. First come to the unidentate ligand. When a ligand is bound to a metal ion through a single donor atom, the ligand is said to be unidentate. For example, this is Cl minus. Only one atom is present and that can able to donate a pair of electrons. Now in case of H2O, this oxygen which has the lone pair of electron is able to donate the pair of electron. In the same case, this ammonia NH3, this nitrogen have one lone pair of electron and it can donate single donor atom. Then that is known as unidentate ligand. Didentate ligand. When a ligand can bind through two donor atoms, the ligand is said to be didentate. For example, this is C2O4 2- oxalate ion. It has two oxygen atoms which are capable to donate the electron pair to central metal atom or ion. Now this is NH2, CH2, CH2, NH2. Its IUPAC name is ethane 1,2-diamine, and in this case this nitrogen has one pair of electron and this nitrogen also has one pair of electron, and both nitrogen capable to donate the pair of electrons. That's why this is didentate ligand. Polydentate ligand. When a ligand can bind through several donor atoms present in a single ligand, the ligand is said to be polydentate. For example, this is ethylene diamine tetraacetate ion. Ethylene diamine tetraacetate ion, and this is EDTA 4 negative charge, and this is its structure. Now in this case, these four oxygen atoms which are negatively charged donate the pair of electron. Along with these two nitrogen atoms, they also donate pair of electron. In this way, 6 donor atoms are present in this EDTA 4 negative. That's why this is a hexadentate ligand, and commonly we use the word polydentate ligand. Okay. Chelate ligand. When a di or polydentate ligand uses its two or more donor atoms to bind a single metal ion, it is said to be a chelate ligand. Actually, when di or polydentate ligand use its donor sites to donate the pair of electron to the central metal atom or ion, a ring structure is formed. Okay, and such type of ligands which form this ring like structure, these are the chelate ligands, and the complex formed, these are known as the chelate complexes, and these are more stable than similar complexes containing unidentate ligands. You can see this is the metal atom or ion, and this is ethylene diamine, or IUPAC name is ethane 1,2-diamine. This nitrogen donate a pair of electron, and this nitrogen is also donate a pair of electron. In this way we will get the one, this is a ring structure, cyclic structure. This is again glycinato. Okay, this nitrogen and this oxygen donate a pair of electron and form a ring like structure. Okay, that's why this ligand NH2 CH2 COO, this is glycinato. These are the chelate ligand, and these complexes are known as chelate complexes. Denticity. The number of ligating groups is called the denticity of the ligand, and on the basis of this denticity we have classified the ligands as unidentate, didentate, polydentate. Is it clear? That's why we can say denticity refers to the number of atoms with which a ligand binds to a metal ion. For example, NH3, its denticity is 1 because there is only one atom which can donate a pair of electron. This is ethane 1,2-diamine, its denticity is 2 because it has these two nitrogen atoms which can donate the electron pair. Okay. Ambidentate ligand. Ligand which has more than one donor atoms but at a time can ligate through one atom is called ambidentate ligand. Clear? It is more than one donor atoms present, but at a time only one atom donates electron pair. For example, NO2- and SCN- ion. This is thiocyanate ion and this is nitrite ion. NO2- ion can coordinate either through nitrogen or through oxygen to a central metal atom or ion. For example, if this is coordinate through this nitrogen, then this is written as Ni2N. Okay, this N is the donor atom in case of NO2 minus. In the same way, if it donor or coordinate through this oxygen, then this is known as Ni2O. Okay, this O refers to this oxygen which coordinates to the metal atom or ion. The same way, this is SCN minus. This is thiocyanate ion. It coordinates through the sulfur or nitrogen atom. If this coordinates through sulfur, then this is known as thiocyanate-S. And if it coordinates through this nitrogen, then this is known as thiocyanate-N. These are ambidentate ligand. Coordination number. The coordination number, which is also written as Cn, of a metal ion in a complex can be defined as the number of ligand donor atoms to which the metal is directly bonded. Again, remember, number of ligand donor atoms, not number of ligand. Number of ligand donor atoms to which the metal is directly bonded. For example, in the complex ion, this is PTCl6. Okay, we can say this 6. This represent the coordination number of this PT. In this case, NiNH3 4. This 4 represent the coordination number of nickel in this complex. Okay. Similarly, in the complex ion, see this FeC2O4 3 minus. The coordination number is 6. How this 6? You can say in this case these 3 are the number of ligands. But this C2O4 is a didentate ligand. It has 2 donor atoms. That's why total number of donor atoms are 6. Hence its coordination number of Fe in this complex is 6. In the same way, this is COEN thrice 3 positive charge. Again, this EN, ethane 1,2-diamine, is a didentate ligand. 2 donor atoms per molecule, and there are 3 molecules. That's why coordination number is 6. In simple way, we can say coordination number of a central atom or ion is determined only by the number of sigma bonds formed by the ligand with the central atom or ion. Clear? Now you can say whatever the different terms we have discussed. This is the one coordination compound, and in this case you can say this CO. This refers to the central ion. Okay, and this Cl and this NH3, these are the ligands. Okay, then Cl is 2 times and NH3 is 4 times. 2 plus 4 is 6. This is the coordination number. Okay, and this central ion along with these ligands, this piece or this is known as coordination entity. If this coordination entity is enclosed in this square bracket, then we can say from this to this along with this charge, this is known as coordination sphere. Okay, and this outside the coordination sphere, this is ionizable anion, and this is also known as counter ion. Okay, coordination polyhedron. The spatial arrangement of the ligand atoms which are directly attached to the central atom or ion defines a coordination polyhedron about the central atom. Simply we can say this represents the geometry of this complex. The most common coordination polyhedra are octahedral, square planar and tetrahedral. For example, this CONH363 plus, this is octahedral, and this is the shape of this octahedral. This is NiCO4, this is a tetrahedral, and this NiCO4, this is a tetrahedral. Okay, and this is PTCl4 2 minus, this is square planar. This can be represented like this is a square planar, and these some geometries are also, this is trigonal bipyramidal and this is square pyramidal. Okay, these are the geometries of coordination compounds, or these are also referred as coordination polyhedron. Oxidation number of central atom. In the 11th standard, we have discussed how can we find out the oxidation number. Okay, same rules we will apply here. The oxidation number of the central atom in a complex is defined as the charge it would carry if all the ligands are removed along with the electron pairs that are shared with the central atom. For example, oxidation number of copper in this is +1 and it is written as Cu first. How this oxidation number +1 came? We can say again, if you remember, that is, if we are having any complex ion, then sum of the oxidation number of all the species is equal to charge on that complex ion, okay, or on polyatomic ion. In this case, we can assume that the oxidation number of copper is X, then plus there are 4 number of Cn and each Cn have one negative charge, and this is equal to -3, which is the charge on this ion. If we find out the value of X, it will come +1. Okay, in this way we will calculate the oxidation number of central atom or ion. Homoleptic and heteroleptic complexes. Complexes in which a metal is bound to only one kind of donor groups are known as homoleptic. For example, this is CONH3,6. Only this is one kind of donor group. That is, this nitrogen is only one kind of donor groups. That's why this is homoleptic. Complexes in which a metal is bound to more than one kind of donor groups are known as heteroleptic. Okay. Now in this case, we can say this is nitrogen, along with this is chlorine. These are the more than one kind of donor groups. That's why this is heteroleptic complex. Okay. Thank you. Subscribe my channel to get the new videos of this chapter.